So we have Pierre Rigaud, who is a product manager for medium and high voltage products, and Nawar Shubbar, who is regional manager for the Middle East region. Okay, so the session today will be about insulation class and temperature rise class. We will do an overview about what we are talking about, and also we will cover why the topic is important in terms of specification and the impact it will have on a given project or on a given machine specification.
Hello, everyone. And we will start this discussion really from the basis, so back to basic. And here we just want to remind you that an electrical rotating machine is an energy converter. And as you know, we are converting mechanical energy to electrical energy. And of course, in the process, Mother Nature will take its toll, and that appears in the form of losses. Those losses will be generated inside the active part of the machine, and those losses will appear in the form of heat. And this heat will be dissipated to the ambient, to outside of the machine. And the way it is dissipated will lead to different thermal state of the active part of the machine. So if we jump to the next slide, here, what we would like to point out is that the thermal state of the machine, so the maximum operating temperature of the machine, has a great impact on the design of the machine and on the size of the machine. So here we have given an example of a 3.3 MVA machine, 4-pole, 400 volt, 50 hertz, running in a 40-degree ambient. And if we want to design this machine and we say, okay, because of the different equipment and the different material we have in the machine, we cannot go above the temperature of 145 degrees inside the machine, then we will have a machine that is, we will select a machine that is called LSA 54.2 M10, and a machine that has a mass of roughly 7.9 tons. If now we say, okay, the maximum temperature can be a little higher, 165 degrees, then we will select a smaller machine, an LSA 53.2, which has a mass of a little less than 7 tons. And now, first of all, those machines have different size. You see that with higher temperature, maximum temperature, we get a smaller machine, and we also get an impact on the price and on the cost of the machine. So here we are talking about a roughly 13% price difference between those two selections. So what does it tell us? It tells us that this maximum temperature criteria is very important. So the next question is, how do we define it? Why should it be such a temperature? So for us, what is very important is to understand where are the thermal sensitive components. And those components, which are organic components, are mostly present in the insulation of our machine. And in the insulation system is, of course, in the hottest place of the machine. So here we have given the example of a random winding on the left-hand side where you can see the winding. And for example, the turn-to-turn insulation, the enamel is thermally sensitive. And on the right-hand side, we have the high voltage form-wound winding where, for example, here, the taping that is on top of the coil, which is a polyester mica tape, is thermally sensitive. Now, if we want just to get an idea of how many components we have in our insulation system that are thermally sensitive, well, here you see some cross sections of slots with the insulation system, and we have highlighted with this red star all the components that are thermally sensitive. So those components will be the component that will define the maximum temperature that is acceptable inside the machine. And to help us in selecting those components, in classifying the operating temperature of the machine, we are using international standards that will create category of material that can work in certain temperature and category of machine that will operate in certain temperatures. And I will pass the microphone to my colleague Nawar, that will explain you those two major standards.
So I'll go through the definitions of both insulation class and temperature rise class, and then I will talk how we can use these definitions really in real life and what it has as an effect on the lifespan of the life expectancy of the machine, durability of the machine, and then I will talk a bit about a real life example of what kind of specification is available in the market and what we get on daily basis. So without further delay, so the insulation class, there are many types of insulation class used for rotating machinery, and we're talking here about all rotating machinery, including motors and alternators. But the most commonly used are insulation class H, F, and B. For alternators, you know, it's mostly H and F. And we have a standard, an IEC 60085, that defines the temperature class of all these insulation class. And as you can see from the table below, we have insulation class H with temperature 180 degrees, F with temperature 155 degrees, and B with 130. What does that mean? Again, we go back to the standard IEC 60085. The 180 degrees or 155 degrees is the maximum temperature at which the life expectancy, the theoretical life expectancy of the insulation will not be less than 20,000 hours. So for insulation H, even if the winding temperature of the insulation material temperature reaches 180 degrees, the minimum lifespan of the insulation should not be less than 20,000 hours. Same thing for F, even if the temperature reaches 155 degrees, the life expectancy is 20,000 hours. From that, we can immediately understand that the insulation class H is superior to insulation class F and B. And that's why Leroy-Somer has decided to harmonize the insulation for all its machines. So all the Leroy-Somer machines come with insulation class H. This is something I wanted to highlight because in the market, other manufacturers use still use F insulation for their machines as a standard and offer H insulation as an option. Next definition, which is also very important in defining, sizing a machine, is the temperature rise class. So temperature rise class is defined as per IEC 60034-1. And the definition says, you know, it's the maximum temperature increase over the ambient temperature of the machine when it's running at nominal values. So nominal power, nominal current, nominal voltage. And in this standard, there is a certain temperature increase allowable for each temperature rise class. So for temperature rise class H, it's 125 degrees above 40 degrees. So going back, if you to the slide that Pierre showed you. So here the temperature, the design temperature of the machine should be 165 degrees maximum. For the F class, it's 105 degrees above 40 degrees. So the maximum design temperature is 145. And for the B class, it's 80 degrees. So the maximum design temperature of the machine is 120 at 40 degrees centigrade, which is typically the ambient temperature taken into consideration when sizing standard machines, including Leroy-Somer machines. So why we are saying 40 here? Because maybe you will ask the question, Mr. Leroy-Somer, we are in the Middle East, and the temperature, ambient temperature here is 50 degrees and 50 degrees. So let's say we have a machine with an temperature rise class F at 50 degrees. So here, the temperature rise above the ambient temperature will be limited to 95 degrees. So again, we will oversize the machine. We will design the machine in a manner where the maximum allowable increase in the temperature will not exceed 95 degrees. Okay, so we've defined the insulation class. We defined the temperature rise class. Now, in practical life, what does that mean? This will be explained in this slide. Just to highlight, as you all know, rotating machinery are all about thermal margin, about thermal reserve. So as long as the thermal reserve is big, it's large, that means your machine is highly durable and its lifespan will be long in more than tens of years, let's say. So what is the thermal margin? So the definition of this thermal margin, and here is, it's the insulation class temperature minus the operating temperature. So what is the insulation class temperature? I'll just refresh your memory. Insulation temperature is 180 degrees for insulation H, 155 degrees for insulation F, and 130 degrees for insulation B. What is the operating temperature? This is what we talked about when we defined the temperature rise class. So it is the temperature rise class plus the ambient temperature, which I will take as 40 degrees centigrade as per all standard alternators. So here, if you read in a data sheet or a specification that the alternator is a class HF machine at 40 degrees, the first letter H is the insulation class, and the second letter is your temperature rise class. If you look at the graph on the right-hand side, you will see this example is for a class HF machine at 40 degrees. So if it's a class H insulation, that means its temperature for the insulation class is 190 degrees. The ambient temperature again is 40 degrees plus the F temperature rise, which is 105, that gives us 145. So the operating temperature is 145 and the margin is 180 minus 145, which is equal to 35 degrees. And this thermal margin really defines the lifespan of the machine. So going back to daily inquiry, daily specification that we see, most of the time, especially for oil and gas application, we see that the requirement is for a machine with F insulation class and B temperature rise. And we always try to explain to our clients and to our end users that if we propose an HF machine, so an insulation H temperature rise F machine, it will be exactly the same in regards to the lifespan. So, but the machines will be totally different, and I'll explain to you why. So let's look into the graph on the right hand side. We'll see that we have a machine which is H and F. Then the insulation class temperature is 180 degrees. The temperature rises F, which is 105 plus 40 degrees, that's 145. We do the simple math, then the thermal margin is 35 degrees. Again, we go to the FB machine. So F insulation class temperature is 155. The B temperature rises 80 plus 40 is 120. 155 minus 120 equals 35. So basically, these two machines have the same lifespan, but as Pierre showed you in his first slides, one machine is designed at operating temperature of 165, will be smaller, will be lighter by 1 ton, and will be cheaper. The other one will be heavier, 1 ton, will be bigger. And this is not just, here, if you select the correct machine, it's not going to be just saving in the cost of the alternator. A smaller, lighter machine means a smaller chassis, a smaller canopy. This is for the OEM. For the client, it means a smaller installation in terms of foundations, in terms of everything. So smart, scientifically based design is really the right way to size the machine. Over specifying will only be a loss of money. And to be honest, why do we see still the specification as F&B, not H&F? Because these specifications were written at least 30 years ago, where the insulation H materials were very expensive. So most of the manufacturers were using F insulation materials. But now, the H insulation material is available at a moderate or good price, and that's why Leroy-Somer has standardized the insulation material with H insulation class. That's my final slide, and here I pass again the mic to my colleague Pierre, who will go through other aspects of this presentation.
I will continue on the explanation given by Nawar, and I will go more in detail on this thermal margin aspect. As Nawar explained, what we call thermal margin is the difference between the difference between the thermal class of our machine and the maximum operating temperature of the machine. And here we will explain about this Arrhenius law. So Arrhenius, which is a famous Swedish scientist that worked on the temperature impact on the speed of chemical reaction, showed that the aging of insulation material follows an exponential law versus time, and he explained that in a very simple way, saying that if you reduce the operating temperature of a machine by 10 degrees, you will increase the lifetime of the insulation system by 2. Of course, if you increase the temperature by 10, then you reduce the lifetime by 2. And that enables us, to come to this logarithmic graphic that can give a, let's say, a more detailed explanation on the relationship between the thermal state of the machine and the expected lifetime. So here on the bottom scale, you have the operating temperature of the machine, and on the vertical axis, you have the expected lifetime. Here, we are, of course, talking about things that are based on the ISO 66085 standard, which considers continuous operation, continuous operation at a specified temperature. So let's go a little bit more in detail on the red line, which is, or the orange line, which is the insulation class H material. And what you will see is that here, if we operate our insulation H machine with an insulation H insulating system at 180 degrees, we have a thermal margin of 0 degree, so no thermal margin. So we should expect 20,000 hours, which is roughly 2.3 years of theoretical lifetime for the insulation system. Now, if we go further and we say, we see now we operate this machine in what we call the HH mode, which is a machine with an insulation system H running at 165 degrees. Then the operating thermal margin, the operating temperature is 165, the thermal margin is 15K, and if we follow this Arrhenius law and we follow this line on the graph, we'll see that then we can expect more than 20,000 hours. Here in this case, it leads to 6.5 years, and so on. So here we have the very classic HF configuration, where the machine with an insulation H is operated at 145 degrees. So the temperature of operation here is the absolute temperature we find on the thermal sensitive component. So here the thermal margin becomes 35 degrees Kelvin or Celsius, and here we have an expectancy of 26 years, which is something that is very reasonable for prime power application or application, for example, like hydro, where we are running 24 hours, 7 days a week for very, very long time. And now, last but not the least, here we have a machine with an insulation class H, but that is running with a temperaturized B. So the operating temperature, maximum operating temperature in the thermal sensitive component will be 120 degrees, which leads to a 60 degree thermal margin. And then you can see here on this curve, and if you use the Arrhenius law, you will calculate it also by yourself, something like 1.2 million hours of theoretical lifetime, 146 years. So this is for us the opportunity to show that here we have really an oversized thermal lifetime. Now, here in this table, we try to summarize what was visible on the curve. And here you have on the left-hand side the insulation class lifetime depending on the operating temperature. And on the right-hand side, you have the same for the insulation class F. And what is very important to see, first of all, is that if you look at the HF system, so insulation H, running at temperaturized F, you should expect the same lifetime as if you have a machine with an insulation class F, running at a temperature rise of B, this 26 years. So as in Leroy-Somer we have an insulation system H, we would recommend to use a temperature rise F and not B. And here what we conclude is that HB will lead to an oversized insulation system, and as Nawar explained, it also means a larger machine and a more costly machine, which is not needed in this case. And then what we would recommend is to use this HF over the FB machine, which makes a more compact machine and a more cost-effective machine. Now let's try to summarize all the topics that were covered. First of all, what we have explained is that the key elements that are thermally sensitive in our machine are the insulation material, which are the organic material located in the hottest places in the machine. Here, what we are saying is that the operating temperature and the insulation class are really key sizing parameters, and this is why we really, as machine designers, are looking for the temperature rise and the cooling medium temperature and the insulation class to be specified or to be explained or to be provided with the RFQ or within the technical specification. And of course, this can lead to discussion with you to really understand and provide the most optimum and adequate solution for your application. We have explained about the Arrhenius law, so this 10-degree law, and we have also talked a little bit about why to select such thermal margin, because the thermal margin, as Nawar said, is really the key element. And what we say is that for prime power application, we would go for a thermal margin of 35K, this HF configuration, which provides a long lifetime and a larger machine. And if you have a standby machine or machine that will run a very little number of hours per year, then it makes sense to go for an HH or an H 180 degree design, which provides a shorter lifetime, but a smaller machine and a more cost-effective machine. And of course, just to conclude, as all our machines are manufactured with an H insulation class, we recommend to use HF or HH machine for best economical compromise.